Welcome for another episode of Quadratic Sieve running on Java. My name is Ilya Gazman. Let's hack. First, I want to thank for the commenters who suggested to use a bigger text size. So I'm using 150% zoom. And I'm going to use a presentation mode in IntelliJ. So I hope you will get a better results. Cool. So this episode we are going to talk about Dixon method, but before that, let me talk about the previous episode stress tool that we've been running. Actually, it's not such a good idea to run the stress tool while you record. So this is why the values were so screwed. So the true values is 6031 for the small k number optimization. The trivial division is actually faster than Fermat methods and the Congruence of squares. Cool. So now let's move to a Dixon method. With Fermat method, we have been looking for numbers where the square minus n is also a square. Then we switch looking to sequential numbers, starting from square n, and we added a Congruence of square optimization, where we're no longer searching for a square minus n equals square, but where a square mod n equals a square. All right. So now we are moving to Dixon method, and in Dixon method we are weakening the condition even further. We are saying where square equals to e. What is e? E is a product of small factors bound by some constant b. And we are calling for each such combination a relation or b smooth value. We need to find b plus 1 such relations so we can form a congruence of squares. So this is what we are searching eventually and extract a solution. How those b smooth values help us? We are looking. Here's an example. So let's say we found some b smooth value equals to that. It's not a square, but multiply it by that value and you get a square. So basically, another way to look into it is take all the non-even square powers, so 2 power 3, and we need to find the value where the 2 will have also odd power. So 2 power 3 multiplies by 2 power 5 equals 2 power 8, 3 plus 5. And similar here, 1 plus 3 is 4, 8 plus 0 is 8, 6 plus 0 is 6, and we are getting a square, which is 8 divided by 2 is 4, 4 divided by 2 is 2, yeah. This is a solution. Actually, we can have a nicer example, so let me run through that example first. We are picking a number that we want to factor, this number, some b bound 7. So it's all the vector, so all the prime numbers up to 7. So it's 2, 3, 5, and 7. Then we are starting from square n, which is 292, and we are searching for b smooth values. 513 and 537 are such values. And when you're multiplying them, you're getting a square. So the solution is going to be the multiplication of those two values. So that plus the square of this value, which is this. GCD with n and the result is, well, the factorization of the number. Obviously, we can have more than one relation, and to solve those, we need to use a Gaussian elimination. To simplify it a little bit, we don't really care about if it's 2 power 5 or 2 power 7. All what we care if it's an odd or an even square power. So we can transfer it into a vector, saying that we're only searching each power which is odd going to be 1, and each power that it's even is going to be a 0. So 3 mod 2 is 1, 1 mod 2 is 1, 8 mod 2 is 0, 6 mod 2 is 0. And when we are multiplying those numbers, we can actually say that it's similar operation for XORing, because 1, 1 will be equal to 0, 1, 0 will be equal to 1, and so on. So the XOR will give us 0, 0, 0. So the 0 vector is a solution. And we can find those 0 vector or null space efficiently using a Gaussian elimination over base 2. Wow, I hope that you understood that. It was a little bit challenging for me to explain. If you have any questions about it, please ask me in the Facebook group or post below. And the source code is going to be available in GitHub. During this episode, I'm going to implement the first part of it, of searching for B-smooth values. And next episode, we are going to implement the Gaussian elimination. All right, so let's go to the code. This is the congruence of squares with the small k optimization that we discussed last time. So I'm starting episode, I think it's 4 now, with that. So let's see what we have so far. So we are picking up a square, which is n multiplied small integer k. Then we're iterating over a small I value, adding it to our square. This is a. Then making power 2 mod n, and hoping that this value is a square. So now the condition can be weaker. We can look if it's the smooth value. Let's call it value. And if indeed the case, then we need to collect them. So we want to collect A and mod. So we will need a new structure for it. Let's call it be smooth, and we will have A and B values here. Create a constructor for those two. Right, and now if it's a smooth, then we want to be smooth values, and new smooth A and the mod. So that is going to be a list of the smooth values. All right, we are collecting all of those values, and then once we have these smooth values bigger than our bound B, so the bound value, it's dependent on the bit length. Yeah, so let's not make it a constant. Let's make it a so let's start with v equals to 100. The actual optimal value for it is the power of that expression, but when I've been playing with it, it didn't work very well. The best approach is to experiment and find what is the best value for your algorithm. So let's start with 100 and we'll just test it. The only thing that it's important to remember that if you're making a mistake in picking this number, it's better to pick a number that it's too higher rather than too smaller, because too smaller values will have a big impact on performance. Okay, so if we indeed found a b-smooth value bigger than b, then we need to solve the matrix, and we are done. So we need to break this loop. I want to break this one. Let's convert it into a method. So let's call it find b-smooth values. Cool, and let's make a term. Okay, so here we found the b-smooth values. What I'm missing here is the vector. So we are testing if it's a smooth value, but it's not enough. I want that to return the actual vectors that we can use. In Java, we have some really nice structure, which is bit set. And bit set is a vector of bits. So it have a very efficient implementation of XOR and AND operation. All the I don't remember how it's called, but all those basic operations. So this is the vectors that we want to have. Yeah. And let's say if vector is not now, then it's an actual result. And we want obviously to save the vector. So add it to the constructor. Cool. Um, yeah, and now let's implement the test for if it's indeed in the value. So we need to check if this value is made out of our vector base, which means that we need to create a vector base. So let's build vector base. So B is our bound. And let's create some P equal to the first prime. And then it will always be the next prime. And while doing that, we have our prime base. And we will add P. So our primes are probably going to be smaller than the integer space. So let's use the int value for them. Yeah, I'm not sure if we need to use int value or big integer. We'll see later on in a moment. Okay. So prime base. Yeah. So we created our prime base. Now let's check if the value is a bismuth. So while value mod bismuth for bismuth prime base prime. So we need to check if value mod prime is equals to 0. Value of prime. And then value divide e, and if value equals to 1, then we are done. Then return vector, which we need to build, and otherwise return null. Now we can have multiple factors of p. So let's count them. For each such value that we found, let's do a count plus plus. Let's make it a while. And after we're done, we have the count, and this need to go someplace else. So make it into a bigger condition. Like that. It's going to be outside the while loop. Cool. And now our vector is set vector you can just leave it like that. You don't have to initialize the capacity. It will create the capacity in real time, so if it filled up with zeros, it will actually be smaller than b lengths and still work. So let's work with that. And let's use indexed loop, vector set, index I for primes, and the value is going to be a count not to if it's equals. Oh yeah, I can do it like that. Count mod 2 equals 0, then it's going to be true, otherwise it's going to be false. So I can just do it like that. So if it's even number, it's going to be true. If it's odd number, it's going to be false. This is how we are set the vector. And then we return it. I think this is it. We need to test it somehow. Um, yeah, so let's see how much time it takes us first to find all the squares um, for 70 bits. It's a good first test. Takes a long time. Let me see what went wrong. Okay, so a small bug from a previous episode. We need to start with k equals 1 because otherwise we're looking into values smaller than n. Doesn't really matter before, but now the squares are going to be smaller than, and a will end up being 0. Not what we want at all. So it's going to stack inside this loop forever. So by switching it to 1, it solved this. So let's try now. Yeah, let's print times. So log these values found. Oh, sorry, I changed that. So let's change it to 70. 7 seconds. So looks like it's not much faster than the previous method, and this is not even including the Gaussian elimination. But good direction. I can promise you that the performance will be better. More cool optimization that will turn that into blazing speed, but looks like meanwhile it's not that fast at all. Yeah, just mean that you will have to be patient until you will see the future optimization that will speed this up. And it's not even a solution. So I hope I don't have any other bugs in here, but if I do, we are going to fix them over the next episode when we will build the metrics to solve the Gaussian elimination, and we will see that this method is actually able to factor numbers. If you have any questions, please post below or ask me in the Facebook group, and the source code is available on GitHub. See ya!